Alright, welcome back. We're going to continue my lecture on our star. We are on, let's see, we are on slide, I apologize, slide 36. So get to slide 36, and we just finished talking about the assignment from Petropower Incorporated. It is also uploaded in week 7. There's a chemistry basics lecture for you to give you more insight into what I mean by dimensional analysis or stoichiometry. If you have any questions, you can ask me between now and next class, next week, or we can just, you can save your questions for next week, and I will be more than happy to go over the assignment in greater detail. Okay, now moving on to go to slide 36. Matter and light are one and the same. Okay, they are one and the same, and I'm going to do everything I can to convince you of that between now and the end of the semester. Without light, you cannot have matter. Without matter, you cannot have light. Alright, at least in theory. So let's talk about that. They interact all the time. They are connected. Slide 37. I'm going to explain to you a theoretical construct of our sun, our star. And I say theoretical because we've never actually been there. We don't have samples for you, but we do have a tremendous amount of information to give you. Well, we are very confident in providing the structure of our sun. Again, it is in gravitational equilibrium. I put this slide there just to again remind you that there's constant gravitational forces applied to the sun, to the star, as nuclear energy is radiating from the core. So both of those together are causing gravitational equilibrium. However, that equilibrium is changing. The star is expanding due to nuclear energy slightly overpowering the gravitational potential energy, the gravitational forces. So there is an expansion occurring, and it's going to take at least another 5 billion years, approximately 5 billion years, before it completely expands and exhausts the nuclear energy. Okay, slide 38 goes on to just point out the fact that contraction stopped a long time ago, about 5 billion years ago, and at the time the contraction stopped and the bully was starting to get some lashing back, the guy that was being bullied was lashing back, retaliating, if you will, started to expand due to nuclear energy. That also caused fusion to begin. The star turned on. When contraction stopped, expansion began, nuclear energy began, causing the star to quote-unquote turn on. So we talk about the turn-on stage of a star. That turn-on stage is also called the beginning of nuclear fusion. You've probably heard of nuclear fusion. Nothing to be afraid of. Nuclear fusion is exactly that. Taking the simplest nuclei, which is hydrogen, and fusing hydrogen. It's very hard to do what I'm about to ask you to think about doing. Take two pool balls, smash them together, and make one pool ball out of it. Make one ball out of it. Well, that's what the sun is doing all day long. Very hard to put two pool balls together and fuse them together. It takes a lot of strength. I don't have it. Maybe you do. But the sun, with all of its gravitational potential energy, is fusing 4 hydrogen atoms, nuclei, to make one helium atom. Okay, we're going to go through that, and the turn on is when it all started. Okay, so the sun's structure, first of all, on slide 40, it is, the radius is 109 times the radius of Earth. The mass is 300,000 times more massive than the Earth. You know we have 60-watt light bulbs, and by the way, we're not making 60-watt light bulbs anymore. You know that it's illegal to make them now. So, well, I think it's starting in February. In the near future, manufacturers will no longer make them. 60-watt light bulbs are pretty bright, but our star is using the same watts. Our star is 3.8 times 10 to the 26 watts. That's 26 zeros. Take that decimal between the 3 and the 8, 3 point. Take that point and move it to the right 26 times. That's how many watts our star is. Alright? That's an estimate, but it's very bright. Very powerful. Alright? Now notice that light, again, I've mentioned it already, travels at a finite speed, 300,000 kilometers per second. And given Einstein's equation of gravitational potential energy equal to the combination of the mass and twice square of the speed of light, you notice that you see quickly that the energy that is potentially in our star is extreme. 1.8 times 10 to the 47 joules. A tremendous amount of energy in our star. Okay. It's structured that way. Slide 41, it gives you an idea of the structure of our star, not in the core, but outside of that radius that I just mentioned to you. Beyond that, we have the solar wind. But those are charged particles provided by the sun, our star, and they go in every direction. So Earth is in only one location and only getting one portion of that solar wind. Thank the good Lord. That's all I have to say. Slide 42. If you move closer toward the core to the corona, the temperatures at which are around 1,000,000 Kelvin. Moving down to slide 43, you see that the temperatures start to decline. To be perfectly clear, the temperatures do decline by a factor of 10, by 1 order of magnitude, in the middle layer, the chromosphere. And then, because of the release, the solar wind, we lost energy. So that's why, theoretically, that's why the temperatures are slightly lower by an order of magnitude. Moving closer to the core, we have the photosphere. That is the part of the sun that we can actually visibly see with our naked eye. Not that I want you to look straight at the sun. Do not do that. It will cause blindness. Okay? But that is the visible surface of the sun. Its temperatures are slightly cooler again, simply because the release of energy is radiating out. It's at approximately 6,000 Kelvin. And let me tell you, ladies and gentlemen, that is a medium temperature of all the stars that are in the universe, okay, that we know of. Then slide 45 shows that when you go within or below the photosphere, you reach the convection zone. This is where the gravitational equilibrium is taking place. The outward nuclear energy met with gravitational forces causing a convection zone, alright, by the rising hot gases. Slide 46, moving on. The radiation zone. I've been mentioning the word radiation to try to get you used to it, comfortable with the word. Yes, it can kill you. Radiation can kill you. And yet, it is extremely necessary for life. The energy from the core is transported radially from the core. Photons is the term we use of how the energy is transported. Slide 47, you show that outward radiation is caused by the nuclear fusion, which turned on approximately 4.5 billion years ago. That nuclear fusion needs temperatures at approximately 15 million Kelvin in order to fuse hydrogen to make helium. Alright. So a lot is going on within the structure, the construct of our star. So slide 48 is a little bit of a summary. The sun shining. Sunshine, sunshine in my soul today. How about sunshine in the star today? Caused by this controlled explosion that we call gravitational equilibrium. Okay? And slide 49, next slide. The structure of our sun. It is very clear that there is a well-defined structure in our star. Now, is it very calm, very peaceful? No. Just look at the picture on slide 49 and you'll know that it is not peaceful. Every once in a while, approximately every 11 years, it goes crazy. It goes nuts. Alright, slide 50 is just a little humor from a friend of mine. This is how we take care of business in San Antonio. Slide 51, we're going to talk a little bit more about nuclear fusion to calm you, to make you comfortable. You can speak nuclear fusion language, okay? So, what is nuclear fusion is the real question here. So slide 53 is where I'm at. Nuclear fusion is not what happens in our nuclear power plants. Nuclear power plants take a very, very heavy element with lots of protons, lots of neutrons, lots of electrons, and splits it. We call that fission. With fission, tremendous power emerges from the splitting of that very heavy element. Excuse me. Not only is tremendous power released, but radiation occurs. We don't know how to handle the waste radiation. So we flush water into our nuclear power plants to remove the waste radiation. Okay, we call that nuclear waste. But what happens in a sun, or in our sun, in all stars, is fusion. Taking two lighter elements, fusing them together to make a heavier element, more massive element, okay, causing them to stick together. And yes, that is why we need tremendous energy to do that. It's just very hard to do that. It's not done on the Earth. Can't be done on a planet. It has to be done on a star. That's where the energy is. You know, the guy that was backed up in the corner for 25 million years, that's the only time it can happen for a star of our mass. We'll talk about other stars later next week. But it's not very simple. You know, it's not like you can just take two hydrogens to make one helium. There's more to it than that. The next slide shows you what occurs at low speeds. Low speeds is repulsion, but with the temperatures at upwards of 15 million Kelvin, you can actually stick, using the strong force, stick the elements together. And the next slide shows you that with 4 hydrogens you can make one helium. 2 of those hydrogens, with each hydrogen has 1 proton in it, 2 of those hydrogens lose their charge, and that's what we call sunlight. The 2 hydrogens that lose their charge is called a release of energy, radiation, nuclear energy released, sunlight. But those 2 that lost their charge become neutrons in the new helium atom. It's very elegant. It's a wonderful process, and I had nothing to do with it. Okay? Nor do I have anything to do with the sun's business. Alright, slide 56 shows you the step-by-step process in order to make one helium. So a lot is going on. It's very complicated. One thing I do want to point out is what is released in the process. There is waste in this process. Waste sounds like a bad thing, but the waste is what we call a treasure on the earth. One waste is sunlight. The positron released from the process, the fusion process, is called sunlight. But there's also something called neutrinos that have been identified over the last decade that is mass lost in the process as well. We lose a small amount of mass in fusion, but the mass isn't lost to the universe. The universe still has that mass, so it's out there. We have a tremendous amount of neutrinos that we'll talk about later. And also we release different wavelengths of light. Different wavelengths, gamma rays, X-rays, ultraviolet rays, and our atmosphere protects us from the majority of the three that I just mentioned in light. We get the visible light, a different wavelength, different small, very, very small band of frequencies and wavelengths of light, and we also get the radio and microwaves of light, infrared of light. So we get certain things that hit our troposphere, but our atmosphere blocks some of the more harmful energy that's provided by our sun, given this nuclear fusion. Slide 57 goes on further to show you what we get out of fusion. What goes in are 4 hydrogen atoms containing 1 proton each, and what we get out is a helium nucleus, gamma rays, positrons, and neutrinos. We do lose some mass in the process. So yes, the star is losing mass and getting bigger, expanding, lashing out, if you will, just giving it all. So we'll have a thought question, slide 58. What would happen inside the sun if a slight rise in the core temperature led to a rapid rise in fusion? Well, the answer is simply the core would expand and cool. That is exactly what's happening today. It keeps burning, if you will. Burning meaning fusing hydrogen to make helium for a predictable amount of time, another 5 billion years. And it is predictable. We can show you, we have a little bit of evidence that our predictions are reliable. Next slide shows you the solar thermostat. So as the star, our core, expands, when gas expands, it cools in the process. Okay, so in about 5 billion years we are going to begin cooling. But right now the star is getting warmer and warmer and warmer, hotter and hotter and hotter, bigger and bigger and bigger, as it releases more and more energy. So in slide 60, that is not what's occurring right now. Temperature is not decreasing because the fusion rate is increasing right now. But there will come a time in about 5 billion years where the temperature will start to decrease, the fusion rate will decrease, the core will compress again to restore its equilibrium state. Okay, we're not there. But this is the case for our star right now. The next slide, the temperature is increasing, the fusion rate is increasing, the core is expanding to catch up to, with all of the mass of our core, it is losing about 0.7% of as each helium atom is made of mass. So it's getting bigger to compensate. So how does the energy from fusion get out of the sun? Slide 63. Well, the authors give you a little bit of an idea. It's a very chaotic, crazy star, and it eventually finds its way out in the radiation zone of the star, and it seems to be random as it finds its way out. It seems to be very very like static charge. It's just unpredictable how it comes out, where it comes out. But we have pictures of the star, and beautiful pictures, I might add, very revealing. Before we get there, the convection zone is where it all takes place. Some of the energy is released to the surface, and we call that solar wind. Next slide. This is an actual picture of the photosphere of our star, where hot gas is reaching the surface. It looks like a bunch of bubbles, like a blister, if you will. That is what our star looks like. You can get more pictures on the NASA SOHO website, but it's incredible what is occurring on our star. It is not a peaceful place. It is extremely violent, and I recommend against anyone trying to travel to the star. Okay. How do we know what's happening inside the star, even though we've never been there? Well, we use mathematical modeling, and we continue to tweak the models, because the models are never perfect. They're made by humans, but they're made by a consensus of scientists that over time continue to modify the model. And the models are great. We've mentioned it already, how the Greeks began using models. Models are extremely powerful, extremely beneficial, so that a group of people all over the world can talk about the same model, the same subject, with clarity. That's what models are great for. Models are not something to completely 100% copy. There's no way I can copy those guys in GQ, for example. There's absolutely no way. They're just a model for me to try to either critique, try to emulate, but never become. There's no way. Look at me. Okay, moving on. We also see quakes that occur on the star. And with the quakes, we can penetrate deep into the star, as far as the core. With the quakes, we can see them ripple through the star. Sun quakes is what we call them. Slide 68. With mathematical modeling, sun quakes, prominences, solar flares, constant observance using SOHO, etc. Even at the McDonald Observatory, they also look at the star on a regular basis when it's a clear day. We put a model together that we can argue against or agree together of what the star looks like. Slide 69 again shows you a reminder that we don't see it all. It is not 100% revealed. With that loss of mass, we also lose neutrinos created by the fusion. Again, that's a new field of research. And the next slide shows you we have some labs funded deep in the crust of our Earth. The Earth filters out almost every single portion of energy that's provided by our star, also provided by our core of the Earth. And the only thing that can pass through the filtering Earth crust is a neutrino. But we haven't been able to find very many neutrinos. You can see the next slide is another attempt at finding neutrinos. How do we look for them? Well, inside these objects that we have deep in the crust of the Earth, we put a pure substance like hydrochloric acid, something pure, and then takes many samples throughout the day upon day upon day, and we know exactly what hydrogen chloride should look like under a microscope. If we find one compound of hydrogen chloride that is slightly different, what could have caused that? Other than a neutrino, because theoretically everything else is filtered out. So there you have it. No, we haven't found neutrinos that way. We have found neutrinos, not that way though. WIMPs, weakly interactive massive particles. That's how we have found neutrinos. Looking at schists, several very thin layers of schists and micas. Over a long period of years of data, we've found a little bit of a change in the construct of the samples, and voila, we have neutrinos that we know exist. I can't hold a neutrino in my hand, but I can tell you that they are all in my hand. They're everywhere. I just can't see them. I can't show it to you so you can visibly see them. They are everywhere. The only way we can identify them is when they actually make a molecule shift in its structure, bump out of an atom. Evidence of a neutrino is everywhere. Just like the wind is everywhere. I can't show you what the wind looks like, but I can give you evidence of the wind. Okay, slide 72 is just a summary of the process of nuclear fusion, taking 4 hydrogen atoms to make 1 helium atom, and in the process we have waste, which we enjoy, called sunlight, and ultraviolet radiation, infrared, energy provided. That's waste from this nuclear fusion reaction. Slide 73, we've also learned about the structure of our star, the sun, how we identify each of the zones: radiation zone, photosphere, chromosphere, solar wind, corona, etc. And then how we use modeling to go farther, to continue to research. Slide 75 is a little more humor. Light travels faster than sound. This is why some people appear bright until you hear them speak. Oh wait, I'm talking a lot. So yeah. Until you hear me speak. I'm a very, very intelligent person until I speak. Well, anyway, it's humorous, right? Okay, a little bit more before we take a break. The sun is definitely connected to the earth, and if you don't believe me, then I'm going to try a little bit harder to convince you, okay? Not only is the sun connected to the earth, my favorite planet, but it's connected to Jupiter. It's connected to Pluto, Halley's, Hale-Bopp. It's connected to the nearest star, Sirius, to the nearest system, Alpha Centauri. It's connected to the farthest most object in space, our sun. Everything is connected. I'm going to continue to try to convince you of that. Okay. How does solar activity affect us? How can I prove to you that we are connected to the sun? Well, we do have evidence of sunspots, solar flares, in slide 78, solar prominences. We have evidence of a magnetic field on the sun. And as I've already mentioned in a previous lecture, we, the Earth, have a magnetic field, which is how we are able to tell you which way is north, and which way is south, east, and west, because of our electromagnetic field. Slide 79 shows you we can actually take a picture of our sun and show you what a magnetic field really looks like at these temperatures. The dark spots, we actually call a dark spot or a sunspot, is where the energy has been released from the sun, called a solar wind. Could be a solar flare, could be a solar prominence, but you actually see the magnetic field. It looks like hair, or baleen, if you will. That's an electromagnetic field, each one of them. You can think of a battery. A battery has a plus and a minus cable, a post on the battery, a plus and a minus. Well, one side of that, each of those hairs, if you will, has a plus, and it eventually connects to a minus, a battery terminal. So think of the sun as having a bunch of batteries, gazillion batteries, that are designed in like slide 80. They're organized, they have a flow to them, what's what we call a magnetic field. Okay, the stronger the magnetic field, the closer each of those fluxes are, and you saw how close they were, like hair veiling. Okay, and along each of those fields, wrapped tightly, traveling at the speed of 300,000 kilometers per second, are electrons. So we have electricity traveling through each of those fields. That's why we now say electromagnetic fields. Slide 81 is another picture of a light looping of bright gas, many times connecting sunspot pairs. The plus and the minus go back to the battery, if you will. The battery is the sun itself. Okay? But sometimes you'll see in this picture alone that not all of them reconnect. But imagine, if you will, you see this arc starting one part of the sun, launching into space and coming back to another part of the sun, can go as far out as Earth. Earth can be caught into one of these loops. They go out way into our solar system. Okay, and slide 82 is an artistic rendering of what we mentioned. The dark spots, the sunspots, are slightly cooler, around 4,500 Kelvin, as opposed to the photosphere at about 5,800 or 6,000 Kelvin. So the loops exist. Loops are good. All right. What's not good is slide 83. Sometimes we have a solar flare. As long as it's not coming toward us, everything's cool. But given an X-ray, looking at our star in the X-ray, we're starting to see a very active star. Slowly, not as fast as scientists would hope or expecting. I guess they don't hope it, but it's not happening as fast as they expected it, but it is happening. They're starting to see more activity on the star, and one solar flare did come our way recently. But that is a solar flare. Okay, slide 84 shows you how violent the star is. It is not a very calm, very peaceful star. As a matter of fact, it's very hard for me to explain this to you right now, but I'm going to. I'm going to try to explain. Look at that star, or any of the pictures on NASA's SOHO website. It is twisting. The North Pole, let me back up. The sun, just like our Earth, rotates on its own axis. But not just like our Earth. It rotates. The North Pole and the South Pole rotate at a certain rate. The center, or the equator, rotates at a different rate, causing a twist in the gas called the sun. That twist completely destroys the construct, the photosphere of our star, approximately every 11 years, causing a maximum number of coronal mass ejections and solar flares every 11 years. Well, we're right at the peak for the next 11 years, for the peak. Started in 2012, but it was too quiet, what they expected. So we're now here in 2014, still watching for extreme activity on the star. It's starting to show up. Okay. We're not that perfect in predicting dates and numbers. So December 21st, 2012 came and went. Anyway, so moving on, what about humans? How are we affected? Well, look at slide 86. You see that? That affects me. Coronal mass ejections. Imagine the Earth intersecting with a coronal mass ejection. So let me explain what would happen if a CME came our way. Slide 87 shows a typical day. Solar wind comes our way. We get sunlight. Our electromagnetic field does a very good job at diverting the sunlight. the electromagnetic intense solar winds are diverted. As they meet with our electromagnetic wave and our atmosphere, we get, as the solar flares meet with our atmosphere, many times we get something called northern lights, or aurora borealis. Slide 88. Beautiful. What's amazing is the phrase quantum leap occurs from this, because plasma, pure energy, intersects with our electromagnetic field and our atmosphere and converts magically, instantaneously, into oxygen, which is the green looking colors on this slide, nitrogen, helium, other oxygen is provided to the earth. That's called a quantum leap. Amazing process. Don't know how it's done. I can't find any research to really prove how it's done, but it's just done like magic. The movies exist online, and I might have time next week to show you a movie. This is a good time to take another break and end our lecture in part 3, the last part of this lecture. So take a break, stretch your legs, and we'll pick up on part 3.